So I'm going to talk about a project at UCSD that is essentially an NSF instrumentation project known as Greenlight. And the Greenlight principal investigator is Tom Defani. And the goal of Project Greenlight is to create an instrumented data center that is a data center that in some sense is self-contained, that has racks of multiple types of computing systems, small clusters if you will, that are instrumented with respect to power and environmental information for every server. And that data is then made available to the various Greenlight computer science researchers who have in common a goal of determining how best to achieve the greatest level of work per watt. So these are investigators that are working predominantly in computer science and computer engineering. They're looking at virtualization, dynamic thermal management, various levels of power management. And one of the projects within Project Greenlight is a DC server experiment, and that's what I'm going to talk to you about today. So we started with 2 Sun modular data centers, filled them with a variety of different types of computers, including general purpose servers, storage servers, but also specialized processors that were specialized systems built from FPGAs. We have a rack full of Convey FPGA-based systems. We have racks of systems that have NVIDIA 285 general purpose GPUs that some of our researchers are looking at custom programming for improving work per watt. And the various researchers in the Greenlight project all have other activities that they're involved with, which are other projects that require computational resources. So the Greenlight project was funded to provide the hardware infrastructure, the metering and monitoring, to provide to researchers who are doing other research activities in metagenomics, ocean observing, microscopy, bioinformatics, and digital media. And we've taken the real-time data that we're collecting while their various servers are running and constructed a web interface to allow access for the measurement information to help them in their work per watt investigations. So moving back a step, this is one of a number of projects at UCSD that have to do with efficient processing, energy efficiency, use of alternative energy sources. So for a number of years, UCSD has been involved in activities to basically generate our own power, increase the availability of power from sustainable energy resources, and of course take advantage of the various energy credits that are available through the state of California. 2 projects in particular have to do with bringing renewable resources to UCSD. One is a contract for a 2.8 megawatt fuel cell, which is scheduled for delivery late 2011. And another is the creation of farms of photovoltaic arrays around the campus, which number approximately 2 megawatt today, and we're adding to that as we go. One of the goals is to marry the Greenlight research activities as a consumer with the producers of energy based on renewable resources. Our fuel cell, for example, uses waste methane gas from a local San Diego Point Loma sewage treatment plant to go through a fuel cell process to generate power. In particular, the DC experiment ideally would be able to use that power. So at the simplest levels, we observed that computers internally use DC power. and that the solar photovoltaic sources and the fuel cell can generate natively DC power. And currently, they both plug into they are both planned to plug into the traditional AC power grid. But what if we could connect them together with smart control capabilities and use the renewable energy as available? So I'm now focusing on the DC experiment, and that's the 2 of the 8 racks in the Sun Modular Data Center have been outfitted with Intel and Sun servers that have custom power supplies that are driven directly from 400 volt DC. At the moment, we don't have direct access to the renewable energy generators, so we've set up, with the help of an Emerson rectification system, our own DC supply, if you will, that takes the campus 480 volt DC AC, generates 400 volt DC, drives Emerson PDU equipment, which is DC 400 volt equipment, which in turn drives the custom Delta and Emerson power supplies, which are in our Sun and Intel servers. The project takes advantage of National Science Foundation funding, as well as funding from the California Energy Commission and peer funding to perform at this stage as a proof of concept as we prepare for the larger scale activity when we can drive our servers directly from the renewable energy resources, the fuel cell and the photovoltaic energy sources. So in summary, we have a 2-rack proof of concept experiment. It's operational today. It uses Nehalem-based servers from Intel and from Sun, and it also uses a Sun Thor storage server. We're anticipating, and I say anticipating because we've only come online last month, and we're still setting up the energy measurement metrics to analyze what we've done. But we're assuming that because of the lack of AC to DC to AC transformations that you traditionally have in a data center today, that we're going to use less energy, and we're going to generate less heat, which in turn will reduce loads on our air conditioning system. And so we're anticipating we're not going to have the conversion losses going from DC to AC from the fuel cell, or the typical DC to DC conversion losses as you adjust to grid voltage, or the 480 volt AC distribution line losses, et cetera, as we move through the power distribution chain through the PDUs and to the modified power supplies. So briefly, this depicts the web-based environment that gives you, if you will, a dashboard graphical interface to the real-time data that's being made available through the Greenlight project. Specifically on the left, you can see an iPad application that will also work from your laptop web browser. On the right, we have an immersive visualization environment, a cave at the Cal IT Institute at UCSD that I work at, where we've created a three-dimensional model of the instrument and data center that you can enter and interact with and access power and environmental data in real time. These are some of the screenshots of the dashboard interface so that you can, in fact, look at the state of power flowing to the modular data center, or specifically look at fan speed, temperatures in the heat exchangers that are between each of the 8 racks of servers. There's a few different views. Just to look a little bit closely, we monitor the chilled water flow into and out of the modular data center, as well as the fan speed and the temperatures in the heat exchangers. We have some visual interfaces that will actually show you a depiction of the current thermal envelope of each of the racks, or the fan speed and dissipation within the racks. And we have a histogram style of view that will allow you for every server. So on the left under legends, each line on the graph depicts a server, and you can see the current heat trends, heat trends over time, over the last 24-hour period of each of the servers. You can identify that some of the servers are running hot. The red is indicating that there's more activity taking place. We also have an interactive view. I'm running out of time, but I wanted to quickly get to the interactive view, which will allow you to, with a mouse, to interactively select a time period and have that time period magnified and give you then specific information about power utilization over that time period, average information for power, etc. So that's in short the information available from the Greenlight instrument to support research in work per watt activities.